All right, guys, we are starting vectors. Okay, so all a vector is in the abstract, right? We're just going to look at basic examples of a vector in terms of how we sketch them and how we manipulate them, but they actually mean something in physics. We're going to see some cool applications soon. So a vector is officially defined as a directed line segment, right? So it has to have a direction and a magnitude, which as we make a sketch, the longer it is, the larger the magnitude. And of course, it's pointing in a certain direction. So it's a linear relationship and it's pointing in a direction. And we're only going to sketch vectors on two space, x-axis, y-axis, flat surface, a plane. We will not sketch in three space, three dimensions. We could, but we won't, not for this class. All right, so that's all a vector is. Before we even start, though, let me go ahead and say this, and I'm going to say this multiple times. If you have two vectors, pretend that those two vectors I just sketched have the exact same direction and the exact same magnitude. They are the same vector. I know they're not the same object. They're not the same arrow, but they are considered the same vector because vector is a magnitude and a direction. Okay, we're going to do more with that. Are those the same picture? No. But are they the same vector? Yes. Subtle, and it matters, and we'll come back to that. Okay, so the first thing we need to do is you need to be able to put any vector in vector position, standard position, different names for it. So a vector can be floating anywhere. It can be floating off in the first quadrant. It could be in the fourth quadrant, whatever. But when you're going to actually numerically force it to be in standard position, meaning the initial point is going to be on the origin. The terminal point will be at A, B, and when that happens, right, you'll actually denote or write the vector as, this is vector bracket notation, AB, or AI plus BJ. A to the left, up, B. So your I tells you units left and right. Your J tells you units up and down. So we actually, for example, if this is 3, then this vector right here is actually vector I. So when I write 3I, that actually means a vector that goes there. 3 times as long as I is 3I. And then J is the vector that points straight up 1 unit. Okay? So everything can be written in terms of little vector I, which is positive to the right, and little vector J, which points up. Okay? So when you write this, you're saying a lot. A bunch of I's and a bunch of J's form this vector. And we'll sort all the details out. Writing it's really basic, though, really easy. So you're just going to write it like this or like this, and we'll do several examples to kind of make sense of that. Okay, so the actual formula. So you have an actual formula for taking any point that represents the initial position, right? P1 represents the initial point. P2 is here. Okay, so if this vector is floating out in space and I want to move it so that it's here in standard position, this formula will do it for me. So it's really basic. Let's do an example. And I'll actually sketch the example so we can see why this will take that vector and move it, not changing the magnitude, not changing the direction. Okay, so let's see. Make a sketch. Okay, so P is at -1, 2. There's P. Q is at 4, 6. Okay, so there's Q. So my vector is, our vector is described as P is the initial, Q is the terminal, but I want to put it in what's called vector form. Okay, in the form AI plus BJ, the formula says all I have to do is take my x values and my y values and subtract. So the formula says take these values and subtract. My x values, order matters, subtract my y values. And that will change the position of the vector. It doesn't change the length or the direction, it just changes the position. So I'm going to take 4 minus negative 1 according to the formula. 4 minus negative 1. 6 minus 2 according to the formula. And that gives me 5, comma, 4, final answer. Or in the form AI plus BJ, that's going to be 5 of those and 4 of the. Wow, there it is. Now, I want you to see physically what that actually did. We took this PQ, vector PQ, and we actually moved it so that it's at 5, 4 in standard position. So it's here now. And if I had sketched everything correctly, it would look like the exact same direction, the exact same magnitude, we just shifted it. Okay, so this formula takes a vector that's floating anywhere and it just orients it so that the initial point is at the origin. Pretty easy, pretty basic formula. Okay, so that's one of our basic skills for the day. So here are a few more. Okay, so to add numerically, to add vectors, really basic. Now, what does it actually mean when you add vectors? We're going to see an application of that. It's actually pretty cool. To subtract vectors, you subtract in the obvious way. Subtract the components. We're going to do an example. When you multiply a vector by a scalar k, just a whole number or just a real value, could be square root of 5, but generally it's just some value. If I want to double the velocity, I multiply by 2. I literally take the vector and I multiply by 2. So we're going to do scalar multiplication. And then if I want to find the magnitude, it's just the first component squared plus the second component squared. Take the square root. So it's just the Pythagorean theorem. Okay? Make a quick sketch of that. So if that's A and that's B, we're looking at vector, let's call it vector V. It's AI plus BJ. Well, what's the length of this vector? We're using the double bar notation now. So double bar V, double bar, this means magnitude. So the magnitude of V would simply be the square root of A squared plus B squared. Okay? So this is what we were calling modulus in the complex plane. We were calling it R in the real plane or the coordinate plane. So same business, different name, right? Different application. All right, so let's do an example of each. So let's find the magnitude of vector V. So I have two vectors that we're looking at. Let's find the magnitude of vector V first. So it's going to be the square root of 2 squared plus 3 squared. And you're thinking, why is this man teaching this? This is so basic. I know it. Consider it an easy day and enjoy it. Wow. So the length of that vector, if I were to sketch this vector, the magnitude, the length would be root 13. That, you can think of that as the velocity or the speed. That is a typical application in physics. The speed of this object is root 13, and I'm not sure of the direction. I just know that's in the first quadrant, which means it's moving up and to the right. That's what it is. That's what a vector is. All right, let's do B. So when you add vectors, you add them in the obvious way. So 2i plus 3j and 3i minus 4j. So you just combine your like components. So 5i, 3j minus 4 minus j. Boom! Pretty easy. Now, the physical application is really cool. Object 1, in space with no friction, think of it as a blob floating in space, collides with object 2, and now it's moving in this direction with a certain magnitude. It's pretty cool stuff. We're going to see some images, and I'm hoping I can find a cool video to show you guys. That's the same as writing 5 negative 1. Okay, same answer for B. Either one of those are fine. Delta math will toggle between the two. All right. Let's do the scalar multiplication and subtraction. So we're going to multiply vector V by 5 and vector W by 3. So V is 2i plus 3j. And W is 3i minus 4j. Y'all, numerically, this is just dealing with polynomials. What does it all mean? It means that I multiplied the magnitude of this vector by 5, I multiplied the magnitude of this vector by 3, and now I'm subtracting, and there's a cool application for subtracting too. All right, so let's go ahead and distribute. So that's 10i plus 15j, minus 9i plus 12j, and then I combine I, 15j, 12j, 27j, final answer, or 127 vector bracket notation. All right. Too easy, I know it. The last little bit is, a little bit more, but still easy. Let's go. Wow. So unit vector, if I want to take any vector of any length, it could have a magnitude of 0.2, it could have a magnitude of 3,000, but if I want to convert any vector into a unit vector, that means a vector that is in the same direction, but it only has a length or magnitude of 1, all I have to do to build a unit vector is divide the vector by its magnitude, which really means you're going to take 1 over the magnitude. So this is the official formula with the correct notation. I don't know why that didn't. You're going to multiply the vector v by 1 over its magnitude. This will always give you a vector in the same direction that has a length of 1. So let's do an example. Vector v, so if I were to make a rough sketch, -5, +8, there it is. I know that vector does not have a length of 1. It has a length of 5 squared plus 8 squared, take the square root. But if I want to shrink it down so that it has a length of 1, same direction, let's zoom in, length of 1, then I would use this formula over here. If I multiply that vector, which definitely doesn't have a length of 1, by 1 over its magnitude, it will now be a vector in the same direction with a length of 1 numerically. So let's find the magnitude of v first. So -5 squared plus 8 squared equals 25, 64, 89. Root 89. So the length of this vector is the square root of 89, which is a little bit more than 9, between 9 and 10. So to build a unit vector, I'm going to take 1 over the magnitude and think of that as my scalar multiple, and I'm going to multiply by -5i plus 8j. That's it. Pretty basic. So that gives me -5 over root 89i plus 8 over root 89j. So that's my answer, but of course it needs to be rationalized. Now, I want you to trust that if I were to actually find the magnitude of this new and improved vector, it would have a length of 1. But I need to rationalize, so I'm going to multiply the top and the bottom by root 89, and we've done this a lot this year, so we've seen this a lot. So the final answer in simplest form is -5 root 89 over 89i. That's my to the left component plus to the up component 8 root 89 over 89j. One answer, or -5 root 89 over 89 and 8 root 89 over 89. Bow. I'm telling you, if you were to do a squared plus b squared, take the square root, you would get exactly 1. This is a unit vector of v of the original vector. Meaning, same direction, new magnitude of 1. Guys, that is it. It's a wrap. This is just the introduction to vectors, and I hope you have an awesome spring break. Be safe. I will be sitting on my couch for a couple days, and then I'm going to be up wobbling around in a boot. So y'all be safe. Enjoy yourselves. Don't stress. Don't go to Florida. If you go to Florida, don't be around 1,000 people. If you're around 1,000 people, wear a mask. If you don't wear a mask, don't come to my classroom scaring me now. All right, I'm just kidding. Y'all be safe.